Hello and welcome to vodcast number 4 out of 5 on the higher level topic of wave phenomena. Today we're looking at resolution. Here are the assessment statements. And we'll go back to these at the end to check that we've done what we need to do. Resolution is all about looking at point sources of light and being able to see if two point sources of light are actually separate sources or one source. Think of looking at two car headlights from a distance. As the car is close to you, you can see that there's two headlights, but as the separation increases between you and the car, then those headlights seem to merge until you can see just one point source of light. Okay? Now, the important thing is to think that although a source of light might be a point source, if the size of the actual source of light, be it a car headlight or a star, is very, very small compared to the size of the separation between you and the object, between you and the car or between you and the star. That, to all intents and purposes, is a point source of light of almost negligible angular size. However, when that light is detected, it does not appear to be a small dot, no matter how small. Instead, assuming it has passed through an aperture, which is required by any optical source in order to focus it, then it will instead have a diffraction pattern. So if you can look at this diagram, imagine you're looking at a point source of light, parallel light, but it has to pass through your pupil, and then the image appears on your retina. Okay, or this could be a telescope, and this could be the CCD detector or the film, whatever. The point is that instead of getting a single dot, you have a diffraction pattern, just as we looked at in our previous work on diffraction as a single slit. You have a central maximum, which we call the airy disk. Technically, it's actually the distance to the first minimum. Okay, then a minimum, maximum, etc. So look at the single slit work for a greater exploration of this. The one thing to think of is the equation is actually a tiny little bit different. It's still theta equals lambda over d, so theta, the angle to the first minimum, equals the wavelength of the light source divided by the size of the slit, or in this case the width of the aperture. The only difference is it's now multiplied by 1.22 because it's a circular phenomenon instead of being a linear phenomenon. So, okay, fast up. So, here we have two sources. Here's two airy disks which are definitely close together but not touching. This is a clearly resolvable. Here we're getting just resolvable until we move into the non-resolvable. And the boundary condition, which actually appears between these two images, the boundary is when the maximum stretches across the first minimum. That's the boundary condition. So the maximum here of this line, once it passes the minimum of this source, okay, then we say that those sources are not resolvable. So the boundary condition, which is called the Rayleigh criteria, which I really should have written here, I didn't. The Rayleigh criteria is when this maximum passes the minimum here. You can observe this effect, by the way, using your fingers. If you look at your hand, look at it right now, appear to be solid. I mean, there's no diffraction effect there, but as you merge them, you'll see that actually you can just about, can you tell I was just doing it there myself, you can actually just see to get this pattern, this join, okay, the black bridge effect. And that occurs because the very, very faint diffraction image of the two fingers actually merges, and because it comes close together, they add together, they superimpose, and you have this black bridge effect. Now, applications of improving resolution, applications of the equation. CDs store data by a series of bumps or pits, and as a laser passes over the edge of these pits, then it sends a signal to the computer. We'll look at that in more detail in a later topic. CDs, original technology, used a wavelength in their laser of 780 nanometers, just in the infrared. DVDs come along, and to increase the information density, they increase the number of pits by making them smaller and closer together. But the original resolution of the CD laser, not good enough, so the DVD laser has a still red, but a shorter wavelength of 640 nanometers. The successor technology to DVD is Blu-ray. Why is it called Blu-ray? You should be able to work that out. Now that picture there, 2 micrometers, that's getting close to the wavelength of light, which is why, by the way, CDs, DVDs sometimes appear to be shimmering with different colours as the light interferes with its reflection. But we can see pictures which show much smaller sizes, but they're not produced using a light microscope. Instead, they rely on the fact that electrons, as well as being particles as we know them, also act like waves. And as they act like waves, we can use them to produce pictures, but of much, 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 much higher resolution, because the wavelength of these waves is much, much smaller than the wavelength of visible light. Here we have a virus ready to inject its genetic material down this tube into a unsuspecting cell. Only 200 nanometers, so that's a third of the wavelength of visible light. Even smaller, what we can see here are individual carbon atoms in a diamond. Okay? In a diamond, in any crystalline structure, the atoms are all lined up, but notice how the alignment of these atoms is different from the alignment of these atoms, because these are what we call separate grains. But it's amazing, you can see individual atoms using electron microscopy. On a slightly bigger scale, here are 2 images of the planet Jupiter, one taken in visible light and one taken using a radio telescope. Now, it's useful, it's interesting to look at what happens at radio wavelengths. For example, the shape is very different. The scale of these images is the same, by the way, because here we can see the interactions of the solar wind with Jupiter's magnetic field, which causes it to give off radio waves. You can't see that in visible light. That's great, but unfortunately a problem here is that the resolution is much, 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 much smaller. Rather than using light, 500 nanometers, you're using radio waves with a wavelength of 21 centimeters. Theta equals lambda over b, lambda wavelength over slit size, so the wavelength is many thousands of times bigger than the wavelength in visible light. So even though b, the size of your aperture, is bigger, think of a radio telescope compared to a normal optical telescope, it can't compensate for the difference in the wavelength. In fact, if we look at optical telescopes, then we build optical telescopes mostly for their increasing light gathering capability. They can just get more light in a large mirror than you can going through the pupil of your eye, but also there's a much improved resolution. We don't have to actually work out the full equation because it's the same equation. We can just look at the difference in our values of B, the slit size, about 5 millimeters for the pupil compared to, say, 30 millimeters for this proposed telescope design to be built in Hawaii, which, if built, will be the largest single mirror telescope in the world. We can also, by the way, using radio and proposed using light, cheat slightly by using telescopes which are separated, and they act as if, for at least resolution purposes, they were a much bigger mirror. And that's still a developing technology for optical telescopes, but it is used now for radio telescopes to improve the overall resolution. We'll probably look at more on that in the astronomy option. So, conclusion. Sketch the variation with angle of diffraction, relative intensity, 2 sources, diffracted and well resolved, just resolved. So that's basically these diagrams here. And state the Rayleigh criteria for the images of 2 sources to be just resolved. Again, that's this particular slide here. The Rayleigh criteria, really should have labelled it. Light sources are just resolvable when the central maximum of source A lies on the first minimum of source B, which I'm sorry, here. Okay, on that minimum. Applications discussed. Now it's time to go solve some problems. Have fun.